It's been a while since my last video because I've been busy finishing up this project. So this video is just to give you an overview of my project that I've been doing for the past 2 months now. Here's the contents page, and this whole project takes a very nice 117 pages, which I wrote in the span of 2 months. Oh yeah, and by the way, I made this little booklet and stitched it together. And this is not technically the final version, because after I printed this out, I went over it and I found some spelling errors here and there and some little clarifications that could be made. So this is almost the full version, but the full version which I submitted doesn't have the little scribbles and edits that I have done in here. So here are the notations. I would really love to make this into a mostly plus metric, but I just didn't have the time to do so. I probably won't show every single page, just the pages that I like and the pages that I have something to say about. So here I have a recap of classical field theory, and this is very basic. You'll see this in your first lecture on any kind of quantum field theory or just classical field theory course. It derives the Euler-Lagrange equations for field theory. You can see here I have made some edits in pencil, but I of course edited it properly and submitted it without these edits. This section, or rather this chapter, is not so much of teaching as it is more of a recap. So you can see I'm going through things very fast. And I'm not really explaining how to derive quite a few things. Like how to derive the stress energy tensor, or why the Fermi-Dirac statistics require an anti-commutation relation. And here we have classical electrodynamics. So this is pretty much just Maxwell's equations. And here we have perturbation theory. You would see this equation, or rather this formula, in Peskin and Schroeder. And these are the Feynman rules. And this is a very quick introduction on the S matrix. So this is the third chapter on path integrals. And I remember in writing this part, I had a lot of issues with sign errors and imaginary factors, because many different textbooks use different conventions and it can be very confusing at times. I also wished I had recorded my presentation, but I forgot to do it. And for this whole document, as you can see, I've been exclusively using, or rather setting up, the path integral. And that's because I found that in quite a lot of QED introductions, they actually use the canonical quantization, either partly or in whole, which that's slightly less common, but they do use the canonical quantization to some degree, which I don't really like, because I think the path integral is such a powerful tool that you might as well just use it all the way. Here I introduced some kind of shorthand to simplify my calculations, and I don't see this shorthand elsewhere, but it really helped me, and my supervisor was okay with it. So here you see this is a perturbative expansion so that we can get the interaction terms. And here's the shorthand in action. If I didn't have the shorthand now, this equation would easily take up a few pages. And this is a very quick rundown of the LSZ reduction. I had to actually brush up on this because I had kind of skimmed over it in my own learning, but it was quite important for this. And here's the 1PI section, which is actually my favorite section out of all of this. And I didn't think it would be my favorite section because, like I said, I had initially wanted to leave it out because I thought it was just too much to include. But I really enjoyed writing this section because there's just so much math, and I enjoy the mathematical part of physics very much. And there are some very nice looking diagrams in this subchapter, which is why it's also my favorite. The Stringer-Dyson equation doesn't usually get introduced in this kind of context because it's usually reserved for stuff like quantum chromodynamics. But I think it's quite interesting to introduce it here. And here are some very nice diagrams. This is called the Dyson series, and it sums up the 1PI diagrams. And here I give a little brief explanation on why the 1PIs have to have the properties that they do. There are more nice diagrams coming up. This was quite fun to write because it was just very long, but it does make sense. It looks kind of confusing and tedious, but in terms of explaining it physically, which I do later, it's quite intuitive. Here I'm trying to generalize the 1PI to cover any number of particles. And I don't usually see this get done in textbooks because most of it is just calculation, and I think textbooks want to focus more on the concept itself, so they tend to skip over this part. And here's the nice diagrams. These diagrams took me a while to draw, but it's worth it. You can see that there's some kind of systematic process you could take to writing down these functions, and once you do that, it's very intuitive and it's very easy to visualize. And this is the final result that I used later on. And here we actually get into QED itself. So we've laid down the mathematical groundwork, and we have Grassmann algebra here, which is a set of interesting numbers in their own right with interesting properties. One thing that I learned writing this was that the traditional way of explaining it, being that the QED Lagrangian is U1 invariant, is actually kind of a misconception, because the U1 invariance doesn't actually historically give rise to the QED Lagrangian, or rather, that was not the main motivation. The main motivation was rather the need to couple the fields minimally, and in doing that you realize a U1 invariance, not the other way around. And I do actually include a discussion of this in the appendix, which we can see later. I would have loved to talk about the Proca equation here, but I couldn't squeeze it in somewhere, and it would be a bit awkward, so I had to breeze through it and get the Feynman rules this way. I'm quite proud of this derivation of the sine rule, Because like I said previously, in most texts, they do use the canonical quantization, which I want to completely avoid here. So I had to do it via the path integral. And I think it's much more rigorous if you do it via the path integral. And I do think the result in the end looks very nice. This is the result, the Feynman rule. And I have a little discussion on the symmetry factors in quantum electrodynamics, which most textbooks also don't cover. And here are the collated Feynman rules for quantum electrodynamics. There's also differing conventions on all of these, so it can be a bit confusing, but I like these conventions that I chose because I find them to be the most prevalent, especially when you compare to texts like Peskin and Schroeder, which are the standards these days. Here we have some computation, and here we talk about crossing symmetry, which is quite an interesting topic in its own right. And this section was the most math intensive for me, but really it was also quite fun to write. Like I said, I really like the math in physics, so for me the more the better. And here I also talk a bit about the mass scale. I believe it's also called the T Hoof mass scale, and I talk a bit about its physical significance. This mass scale has quite important implications when it comes to discussing quantum gravity also. It's one of the things you can point to prove that quantum gravity is, well, in the naive sense of a field theory, is non-renormalizable. And that's actually what makes gravity so hard to quantize. And I really love this section also, because in textbooks like Peskin and Schroeder, they don't really go through the derivation too much. They just give you the bunch of formulas. But evaluating these formulas for myself was very enriching. And from here, I actually used a bit of my own knowledge from general relativity, and it turned out well. It turned out it was correct, so that's nice. Yes, and here are the integrals that get presented in Peskin and Schroeder, and that's how I derived them. I also give a derivation of this, but it's in the appendix because it's very long. And also, I derived the Feynman parametrization from Schwinger parametrization, and that's also not really done in most textbooks. So this whole document has a common theme of me going through textbooks and finding what I don't like about those textbooks and fixing what I don't like about them in this document itself. So I think it's really good if you're like a student trying to learn it for yourself also, and you find the explanations in textbooks not enough, because I had the same experience writing this, and I would say I explained it quite well. Here's a lot more math. This is the dimensional regularization of quantum QED loops, and it's tedious, and there's not much new physics, it's just all calculation, but it's also quite fun. And this is the nice result. The results are always very satisfying, and I really wanted to elaborate on this and how it's gauge invariant, but I didn't get enough time or the correct context to do it in this document. You might notice there are also some things that I left out. Things like Furry's theorem and things like the ward identities, which I didn't get to include. But I do use them somewhat implicitly, especially the ward identity. And here's talking about renormalization schemes. And this part is quite fun to write also. I really enjoyed writing the whole project, really, because quite a lot of it was going through my old notes and polishing it up and learning new things in the process. So it wasn't too difficult because I already had the starting point from my notes. So I wasn't learning quantum electrodynamics from ground zero, but I was still learning and understanding quite a few new things about it. And here I derived the on-shell renormalization schemes, which also in Peskin and Schroeder doesn't get derived. So I'm quite proud of this. Here's the classical discussion of the magnetic moment. You would probably see this in something like Griffiths and in an undergraduate course. And here's the anomalous magnetic moment. I like this epilogue also. It was quite fun to write. I realize I'm saying it's quite fun to write for almost everything now. And I split up the epilogue into like a theoretical discussion and an experimental discussion. So this is the experimental part. I'm talking about using QED to test for any physics beyond the standard model. And these are the references. My main ones were this one and this one. So 1 and 3 are the main ones, along with number 4, but more so 3 than 4. So 1 and 3, and then maybe 2 and 4. And I did use this is a very old, very old text, but it was good for the path integrals. And you can see the appendices for a bit. I didn't do this too rigorously. There's a more rigorous derivation of this, but this is pretty much the simplest way you could do it, because I didn't want to write too much also. And here's the discussion on the U1 gauge invariance of quantum electrodynamics. And you can pause to read it, but I pretty much argue that historically the way that it was derived is not the way that we present it in textbooks, and the way that we present it in textbooks is actually quite flawed. So feel free to pause and read it. And here are the identities that I said I would derive in the appendix. And I believe this is the final appendix. No, there's one more. This is the second to last one. So there's the Schwinger parametrization. And this is the last appendix. And that's it. 118 pages of physics that I wrote in 2 months. And I'm quite proud of it. Yeah, and I binded it. So I plan to in any more publications or any more papers that I write in my time in undergrad, I plan to bind them together and create a nice booklet. But this is what the booklet looks like for now. It has 6 little, what they call signatures in the binding industry. There are 6 signatures, which are these little booklets. And each of them have 20 pages. So now there's 120 pages on this, including the cover page. So yeah, that's about it. And I'm thinking of putting this up somewhat as kind of lecture notes or just course notes, because there's nothing new about what I've wrote. It's not any original research, but I think it's quite useful because it does cover quite a few things that most textbooks don't. So if you would like to see that, let me know, and I'll try to find some place to upload it. Alright, that's about it. Thank you.